Hey guys, welcome back. So today we're going to be doing three questions. We're not going to be going in order. We're actually going to be going backwards. We're going to do 17A first, and then 16, and then 15. Pause the video now if you want to try all three of them. If you want to try 17A and come back for the solution, I'll give you the same opportunity when we do 16 and 15. Okay, welcome back. So for 17A, this is actually pretty straightforward, and this is about as simple as it gets. So CH4 plus 2O2 yields CO2 plus water. So we want delta H, delta S of the system, and delta G. So first we got to calculate the difference in enthalpy and then entropy and then the Gibbs free energy. So let's go ahead and find our table of thermodynamic data, which I always have handy. So the way I'm going to calculate the delta H, since table 2 is in this case table 2 is just a set of formation enthalpies, um, Gibbs free energy, formation energies, and standard and the entropy of each thing. So the Gibbs free energy works very much similar. The Gibbs free energy information works very much similar to the delta H information, and that it is product minus reactant if you're just given them from a table. You can also use the formula, um, which let me first calculate delta H and delta S, and then we'll work on delta G, the two different ways you can do it. So for delta H, it's pretty simple. If I find the data here for CH4 for methane, we'll be off to the races in CO2 and water. So for hang on. Yeah, finding numbers very difficult apparently. Here, let me see if I can find them. Oh, it's 2 pages. That's probably why. I was looking at the wrong page. So for CH4, it's minus 75. So, and for CO2, it's minus 393.8. So 93.8. So, and then remember, plus 2 negative. For water, formation is for water, the formation. Wait, I forgot to check if it was in the gaseous state or the liquid state. Okay, it's gas. So it's gaseous water. So for gaseous water, we get the formation enthalpy is minus 224. No, 242 even. Whoops. And then subtract the formation enthalpy of CH4, which is minus 75. So plugging that into our calculator, minus 393.8, subtract 2 times 242 plus 75. We get that the Gibbs free energy change of this, the delta H of this reaction is minus 802.8 kilojoules. Remember units, kilojoules. And then the entropy change of the system is just products minus reactants. Again, the nice thing about all these numbers is that they generally all work in the same way, products minus reactants. So unless they tell you to use bond enthalpy specifically, you can just sort of mindlessly do product minus reactant. So equals delta H. So the for the entropy of each molecule, so 189 plus what is the CO2's one? And CO2's one is, the one for CO2 is 214. Subtract. Remember, because although oxygen doesn't have a standard state Gibbs free energy change or enthalpy change, there is entropy for oxygen, so we do have to take that into account. Remember that. For CH4, it's 186 plus the one for oxygen, which is, I'm sure it is here somewhere. Here it is. Oxygen is 205, which yields us a positive entropy change of 201 joule per Kelvin. Keep in mind. Keep in mind your units. So 201 joule per Kelvin negative 1. And then for the Gibbs free energy, we know that the Gibbs free energy is just, we know the Gibbs free energy is delta G equals delta H, subtract T delta S. However, since we don't know the temperature, we have to do it the other way, which is just using, again, products minus reactants, which yields us a number, which I will calculate for you. So the Gibbs free energy change, remember for standard state elements, there's no Gibbs free energy change because there's no delta H. So for in this case, it would be products minus reactants again, CO2, which is minus 394 plus 2H2O, which is, for the gaseous, it's minus 229. And then plus, no, subtract even, whoops. Subtract Gibbs free energy of the reactants, which is, thankfully, we just need to look for CH4, which is minus 51. So Gibbs free energy change would be minus 3. So minus 394 plus 229 plus 51, which yields us a Gibbs free energy of negative 801 kilojoules. So, and that's the answer for 17A. So the good way to check your Gibbs free energy is right is that if it's less than your delta H, you're probably doing it right. That's what I generally check, because the Gibbs free energy is the total useful energy and not the total potential energy. The total useful energy should be less than the total energy, or equal to it in the very idealist of situations. Alright, pretty simple question. Now let's step things up a little bit. Let's get a bit more conceptual with our understanding. Let's get a bit more conceptual here. So now try question 16. Try question 16. Oops. I apologize. So try question 16 now and come back for the solution. Alright, so presumably what you should have done was first consider the Gibbs free energy. You want to make sure that the Gibbs free energy was 0 at this temperature, or less than 0. So to make our lives easier, we're just going to work with 0. So delta G equals delta H minus T delta S, which we first want to consider this formula, and we know that it's at 1,000 degrees centigrade, so we should use this formula. And we know that for a reaction to be spontaneous, delta G must be less than or equal to 0 for it to be spontaneous. So the first thing we want to do now, unfortunately, we're not given delta H or delta S. So
Yeah, bro, for lunch.
sorry, people entering, um, people entering my room. Anyways, um, the first step was you, where was I? I lost my train of thought. Oh yes, we need to calculate delta G and delta S, delta H and delta S for the reaction. So let's write out the reaction here first. I'm not going to write out how to calculate them because it's more or less the exact same thing we just did like 2 minutes ago. So 2NH3 plus 3O2 plus 2CH4 yields 2HCN plus 6H2O. Right? So I'm going to just calculate delta H and delta S accordingly. So for HCN, so let me just write that. So I'm not going to go through the process of calculating delta H and delta S on camera, though I will, but I won't write it out. Where's my thing? H and then delta S equals. So ammonia. Well, I know for CH4 2 times. So for the products, it's 2 times HCN, which is somewhere on this sheet. HCN is 227 6 times the formation of water. What state was it in? What state was it in? It was gas, so it should be gas. It should be minus 242, subtract 2 times negative 75 plus 2 times. So for ammonia, it is NH3, 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 NH3. NH3 is minus 46. And we get that delta H is negative 756. So negative 756. Negative 756. And then for the entropy change, we get that it is, the entropy change is, so 6 times, so for water, so water it's minus, so for water it's 189 plus 2 times, so for HCN, yep. So it would be the entropy change for HCN is 202. Subtract. I apologize for the long wait. While I calculate these numbers here, I'm not doing it on camera, but rest assured I am doing something. 2 times is the thing for NH3? Oh, it's here on the bottom. Oh, it's a gas, so I do want to be careful. It's probably a gas, so 193 plus. Oh, oops. I may have made a mistake in my calculation somewhere, but that's fine. I can just pull it up on my calculator. Plus 3 times what it is for O2, which is 2O5 plus 2 for CH4. For CH4, where is it? CH4 gives me times 186, which gives me a standard entropy change of 165. Oh, whoops. 165, and then since I made a mistake in my delta H, I just need to make sure that, so I may have potentially made a mistake here for my NH3, so no, I used the right one, just to making sure. So now that we have delta H and delta S, we can calculate the Gibbs free energy, which is, I'm already going to say, so it's negative 756, subtract 10, I think it's 1,000 degrees centigrade, and then delta S, remember to convert your units. It should be, since we're all working in kilojoules, this is in kilojoules, joules, and this is in joules per Kelvin degree. I want to convert that to 0.165 kilojoule Kelvin negative 1, and this should be 273. Okay, and I don't have to do the calculation here. This is going to be very negative, and it's going to be much less than 0. So given that the Gibbs free energy was negative at this temperature, so delta G is much less than 0. Given that it was less than 0, the type temperature was probably used for kinetic reasons and not thermodynamic, because at this reaction, at this temperature, the reaction is spontaneous, and that's how you would answer question 16. The last one is question 15, and it's more conceptual, so let's consider that. So just pause the video if you want to try it on your own, and the answer is now. So based on this sort of explanation, we know that it's endothermic, so delta H must be positive, and given that it is spontaneous, we know that the Gibbs free energy is less than 0. So we can do a bit of sign analysis sort of to work our way to what a logical answer would be. So let's get out some scrap paper. So we know that delta G equals delta H subtract T delta S. Now we know that this is less than 0, so negative equals positive subtract something here, and T is just a scalar, it doesn't matter what it is, some positive number, and I like to put them in brackets just to denote where our variables would be. So the question is asking, is the structure of the original enzyme or in its new form more ordered? Which one is more ordered? So in order for this to be negative, there must be to make this negative, what's the only way to get a negative number if you have a positive number? Well, you would have to subtract a positive number from it, a larger positive number than you had originally. That's the only way you can get a negative number. And since we are told that the reaction is spontaneous, the Gibbs free energy must be negative. So the difference in entropy is positive. And we can use that fact that the difference in entropy is positive to try and answer this question. So if there is a difference in order that is positive, so there is more disorder as you denature the enzyme. Well, that's the technical term for it. Denature the enzyme. so the structure of the new enzyme is more disordered because there is a increase in disorder as so delta S was positive, and we know that entropy is a measure of disorder in the system. So we know that the new form must have more disorder. So therefore, by that logic, the structure of the original enzyme must have more order. So the answer is the original enzyme has more order because of the reasons outlined above. That was a bit of a conceptual question there, and that's I wouldn't say that's typical of IB multiple choice questions. They generally tend to be a lot simpler than that without the explanation. They just say pick one, but it sort of gives you insight as to how you would go about those questions. So thank you very much for watching.